Hello, I'm Willis from Group 13 and we'll be presenting a seminar project on diamond-like carbon. So what is diamond-like carbon? DLC is a class of amorphous carbon materials that exhibit many properties similar to natural diamond, such as high hardness and high resistance and also inertness. In addition to this, it also shares properties with graphite like electrical conductivity and a low coefficient of friction. Unlike crystalline diamond, DLC lacks long-range order, allowing it to be flexible and formed into several complex shapes. The main distinguishing factor of DLC is that it contains a mix of both sp3 and sp2 carbon, which gives it the combined properties of graphite and diamond. The nanoscale structure of DLC shows many nodules of sp3 carbon atoms embedded in matrices of sp2 carbon atoms. This distorts the bond angles by a bit of the sp3 carbon atoms, which adds internal stress to the DLC, which makes it more brittle but also contributes to its hardness. This excess internal stress is also one of its drawbacks, as it can cause delamination in several cases. DLC is produced through vacuum-based deposition techniques like physical vapor deposition, in which the carbon atoms are bombarded by fine-tuning parameters like the pressure and temperature, or by chemical vapor deposition. Common variants include tetrahedral amorphous carbon, which is nearly pure sp3 and offers the highest hardness. The most important aspect of DLC is that the composition of sp3 and sp2 carbon atoms can be varied, depending on the required and desirable properties. You can also dope the DLC with varying amounts of hydrogen to improve its mechanical properties and reduce residual stress.
Hello, I'm Samriddhi Patwari and I'll be explaining the applications of DLC. DLC coding can be used for a wide range of applications, starting with automotive industry. Think about your car's engine. It's a symphony of moving parts, and where there's movement, there's friction and wear and tear. DLC coatings come to the rescue. We apply them to critical engine components like piston rings, tappets, and fuel injection systems. This significantly reduces friction, which means better fuel efficiency for your car and a longer life for the engine. DLC also adds a durable, scratch resistant, and aesthetically pleasing finish to the decorative trims, making our vehicles look good for longer. Coming to the medical industry, this is an area where precision and safety are paramount. The key here is DLC's biocompatibility, meaning it's safe to use inside the human body. We use DLC to coat surgical instruments to make them harder, reduce friction during procedures, and extend their lifespan. Crucially, it's also applied to implants like artificial hips and knees. This improves their durability and reduces the tiny wear particles that can cause inflammation. Even in cardiovascular devices like stents, DLC helps prevent blood clots and improve their performance. Moving to the backbone of our economy, industrial and manufacturing, DLC is a game changer here. Particularly for cutting tools, it enhances hardness and wear resistance, significantly extending tool life and boosting productivity in factories worldwide. It's also vital for molds and dies in plastic injection molding and metal stamping, preventing materials from sticking and ensuring smoother production. Who doesn't love their gadgets? In consumer electronics, DLC plays a silent but a crucial role. For your hard drives, DLC coatings protect the magnetic platter from the read write head, preventing damage and allowing for more data to be stored. And perhaps more visibly, it's used as a protective scratch resistant coating on your smartphone screens and camera lenses, keeping them pristine. Even luxury watches benefit with DLC applied to cases and bracelets for that durable high end finish. Thank you.
Hello, myself Srihanshu Gupta, and I will be covering the part of the use of diamond-like carbon coating to improve the performance and the safety of the orthopedic implants. Let's begin with the challenge: the modern implants. As it stands, the material we commonly use like cobalt, chromium, and the titanium alloy face a tough environment inside the human body. First, they suffer the wear and corrosion. The constant movement and the exposure to the bodily fluid cause the implant material to gradually break down. The degradation lead directly to the harmful ion release. As the metal wears, it releases a tiny metallic particle into the body, which can trigger the inflammation and the even allergic reaction in the patients. Ultimately, these issues can lead to the implant failure, and this not only compromises the patient's quality of the life, but also often requires the difficult and the expensive revision surgeries. So, what's the solution? A microscopic layer of the diamond-like carbon on the DLC. This coating acts as a powerful protective barrier, addressing these challenges in three key ways. It's chemically inert. The DLC layer form a seal that prevents the corrosion bodily fluid from ever reaching the metal implant, maintaining its structural integrity. It's a biocompatible. By completely isolating the underlying metal, the coating stops the metal ions from reaching into the surrounding tissues, which prevent the adverse reaction we discussed. Finally, it has incredibly high hardness and the low friction. This is crucial for the joint implants, as it drastically reduces the wear and tear between the moving part and the preserving the implants mechanics for the much longer. Now we will looking the critical findings from the article, like how we making the cost quoting effective, and the main logical question is how do we make them truly effective and reliable. These slides cover the two most critical findings from the research. The first and the foremost, the adhesion is everything. A coating is useless if it doesn't stick securely to the implant. This primarily challenge has been creating a durable, long-lasting bond. The research shows that the most effective way of achieve this by using a very thin layer of the interlayer of the silicon. The silicon layer acts as a primer, creating a powerful anchor between the metallic surface and the DLC coating. But we can go a step further than the making a coating stick. We can give it a superpowers through a process called doping. This involves the mixing of the trace amount of the other elements into the DLC film to give it specialized function. For example, the silver doping creates a potent antibacterial surface. This is a game changer for preventing dangerous post-operative infections right at the implant site. Silicon doping, which we really mentioned as an adhesion layer, can also mix into the main coating to improve its thermal stability and further enhance the durability. And coming to the overall part, this brings us to the overall conclusion. The future of the medical implant lie in these advancement. The engineered DLC coating, specifically a system that uses a robust adhesion interlayer combined with the functional doping, like the adding silver for its antibacterial properties, represents the optimal solution for the creating safer, more durable, and the longer lasting medical devices.
Hi, I'm Reshu Asati, and today I'll be presenting on solid superlubricity in diamond-like carbon DLC films based on a very recent 2025 review by Zing. My part of the presentation will focus on the second review article, which discusses the advanced mechanism like hydrogenation, doping, structural engineering to achieve long-term stable lubricity. Superlubricity is a state where the coefficient of friction almost becomes zero, meaning two surfaces can slide past each other with virtually no resistance or wear. Zing emphasizes that DLC films are among the best materials for achieving solid superlubricity because they are made up of mixture of two types of carbon bonds. The sp3 diamond-like bonds provide exceptional hardness and strength, while the sp2 graphite-like bonds allow the smooth sliding and reduced friction. In the figure shown, we can see these structures compared. On the left, diamond is purely sp3, while graphite is purely sp2. In DLC, however, has a balanced mix of both. On the right, there is a ternary diagram showing the proportions of the sp3, sp2, and hydrogen. The centralized highlighted region represents the ideal balance point, where it achieves both the mechanical strength and extremely low friction. The structural balance forms the foundation of mechanisms we'll explore in the later slides. According to Zing, the first critical step in achieving DLC's superlubricity is controlling the surface chemistry through hydrogenation. The DLC surfaces naturally contain dangling carbon bonds, which are very reactive and tend to form strong bonds with counter surface during sliding. This results in high adhesion, which directly translates into high friction. Figure 3a shows hydrogen atoms solve this problem. Hydrogen bonds to these reactive sites, passivating them and preventing the formation of strong chemical bonds across the surface. This creates a chemically inert, low energy surface, causing an immediate dramatic drop in friction. However, if the hydrogenation is incomplete, some reactive sites remain exposed. The figure 3b illustrates how these exposed sites react with carbon from the opposing surface, forming hydrocarbon molecules through tribochemical reactions. This destabilizes the interface, increases wear, and ultimately leads to the failure of the super lubric state. Finally, figure 3c compares these two outcomes. Without proper hydrogenation, the chemical wear dominates. Atoms are continuously removed through destructive reactions. With complete hydrogenation, the chemical wear is suppressed, leaving only minimum mechanical wear, which is slow and more predictable. Thus, hydrogenation not only lowers the friction, but also protects the DLC from tribochemical damage, making it essentially the first step towards stable superlubricity. While hydrogenation is critical for initiating superlubricity, Zing's article emphasizes that it is not stable for long-term use. Environmental factors such as oxygen, humidity, and temperature changes can quickly disturb a purely hydrogenated surface. The figure 5 shows doping and structural engineering to solve this challenge. The first diagram shows TEM and STEM images of the self-mated CNX coating after sliding. Several distinct layers are formed: the first reactive layer, the second supportive layer, and an underlying Si3N4 ball. These tribal layers function like a self-healing interface, continuously forming and protecting the DLC pin during operation. The panel B provides chemical maps of wear and track, wear scar of TOF and SIMS analysis. The uniform distribution of hydrogen, oxygen, and carbon nitrogen oxygen species indicates that the dopants and the environmental species are evenly integrated. creating a stable boundary layer rather than a localized wear damage. The panel C demonstrates how catalytic elements like gold enhance the process. Initially, the interface consists of mostly amorphous carbon. As the sliding begins, the gold catalyzes the transformation of the amorphous carbon into graphene-like lubricating films, further reducing friction and stabilizing the interface over time. Finally, the panel D gives a comprehensive overview to multi-element doping, such as aluminium, chromium, or silicon. Works alongside hydrogen to control oxidation, protect the graphite layers, and even encapsulating wear debris inside the carbon shells, preventing additional damage. Together, these four images show how doping and advanced structural designs can make DLCs super lubricative, practical, and stable for industrial applications. The DLC films with super lubricity has enormous potential across many industries, as discussed in the slides previous to this. It has a lot of potential in aerospace, robotics, and mechanical implants. But even after all of this, the significant challenges remain. The significant challenges highlighted by Zing are first, the DLC films often exhibit poor adhesion, as discussed before, to many substrates, leading to cracking or delamination. The producing of high sp3 DLC coatings is costly and technologically complex, and maintaining super lubricity is uncontrolled. Because, as I discussed, the real environment around us makes it difficult for us to sustain the DLC. Future address is focused on addressing these issues, improving adhesion, reducing the production cost, and ensuring a stable performance so that DLC's super lubricity can transition from lab success to a widespread industrial use. This review was based on one of the most recent reviews from 2025, which covers the cutting edge progress in DLC super lubricity research.
Hello, I am Prakhar and I will be talking about current status of diamond-like carbon. Now, diamond-like carbon coatings have moved from lab research to large-scale industrial use. The global DLC market is valued at about 0.7 to 1.3 billion dollars in 2024 to 25 and is projected to grow at a steady 5 to 10% CAGR up to 2030, driven mainly by demand in automotive, tooling, and biomedical sectors. Key companies like Earlycon Belzers, Ion Bond, and Nippon ITF already offer DLC coating services worldwide, showing its commercial maturity. In practice, DLC coatings are used on cutting tools and dies to extend tool life, reduce sticking, and allow faster cutting speeds. In the electronic sector, DLC protects hard drives, MEMS devices, and optical lenses, where thin, hard, and low friction layers are needed. Typically, DLC comes in types such as CH, which is softer but has low stress, TAC, which is extremely hard due to sp3 bonding, and doped DLCs like silicon or doped, which improve adhesion and thermal stability. Deposition methods include FCVA for ultra hard TAC, PECVD for low temperature hydrogenated films, and hybrid PVD plasma for scalable multilayer coatings. The current research trend is toward multilayer and doped coatings since they reduce stress, improve adhesion, and enhance reliability, especially in automotive and biomedical applications. But in biomedicine, while DLC is promising for its wear resistance and inertness, long-term performance and blood compatibility are still uncertain and require more standardized testing before full clinical use. Thank you.